of the CLRS making a video regarding this because this problem is not that easy. Okay, means all the star mark, neither of the star mark problems are easy, but I felt like showing a making a video regarding this because none of the solutions which are available online are clear to that extent. They only give they have only given the pseudocode and all, but the intuitive working or how it is working is not clear. So let me see. Let me show you how it is working. Okay. So it is first of all it is an in-log algorithm. So my approach shall be something like this. The problem asks us to show or to find longest monotonically increasing subsequence of a sequence of n numbers, but initially instead of continuing with longest monotonically increasing, okay, I shall first find a solution which considers only increasing, means not the monotonically part is not there, only increasing subsequence of a sequence of n numbers. I shall find an algorithm for that and then modify that algorithm for strictly increasing subsequence to a monotonical to an algorithm which finds the monotonically increasing subsequence, okay, of a sequence of n numbers. So let me proceed. Sorry. So in the beginning, to find the strictly increasing subsequence, a standard algorithm is there, okay, which is known as the patience algorithm. So how? Let me take a running example. Means I shall be proceeding or explaining the algorithm based on that example. Yeah, it shall be easier to understand. Okay. So let me do that. Let me first write the sequence which I shall be taking. Let me first just informally say what shall the patience algorithm do, and then let me explain how that patience algorithm actually works, means the logic behind its working. Okay, then I shall means modify the patience algorithm so that it can deal with uh, monotonically increasing subsequences. Okay, means the patience algorithm on its own does not work with monotonically increasing subsequences. It shall only find increasing subsequences. So we shall this is the input sequence and it is given in an array. Okay, means the spaces indicate their different numbers. So what our algorithm shall do is we shall scan the input from the left side. Okay, we shall keep on scanning it, and during its process what we shall be doing is that we shall maintain piles of stacks, okay, with their bottom, means their top open, top at the bottom, okay, for that this portion. And then what we shall do is we shall see take a number and check, uh, starting from, we shall give priority to the leftmost stack, okay, and then see whether the top of the element is greater than this element or not. Okay, if it is greater than or equal to, we can put that element into that stack, or else not. Okay, so this thing shall become clear with an example, and if there is no such possible stacks where we can put our element, okay, the current element which we are scanning, we shall create a new stack and put that element there, and it shall be the rightmost stack. Okay, so let us work out the example. So suppose 1 is the first element. So 1, there is not, wait a minute. So initially there was nothing, okay, no stack was there. So we create one stack and push 1 into it, okay. So this is the element. Okay, so then we are done with 1. Next we scan 2. Next what we shall do is that we shall see this is the top of the stack, but it is currently containing 1. Now 1 is not greater than or equal to 2. So what we shall do is we cannot put this element here. So what we shall do it, we shall create another stack. Okay, we shall create another stack. We shall put 2 here and make this 2 point to this 1. Okay, they point to the top of the stack of the previous stack. Okay, now we shall see, take 4 again. uh, 4 can't be placed here, 4 cannot be placed here, so we need to create another stack, and we place 4 here, and we make this 4 point to 2. Okay, now again we scan this 2. Now this 2 can't be placed here because this is not greater than equal to, but this top is greater than equal to, so we place 2 here and make this 2 point to this 1. Okay, the top of the previous step. Now we take 3. Now 3 we cannot place here, we cannot place here, we can place here. Now this 3 is placed here, and we point this 3 to the top of the previous stack. Now we take 1. Okay, we can this we can place it here as per our rule, because this is greater than equal to the top. This top is greater than equal to our current element. I have placed it here. Now next 10. Now 10 we cannot place here, we cannot place here, we cannot place here. We create a new stack and place 10 there. Okay, now we make this 10 point to the top of the stack of the previous stack. We take 0. 0 we can easily place here because this top of the element is greater than equal to uh, the current element. Then we consider 6. 6 we cannot place here. 6 we cannot place here. 6 we cannot place here. But 6 we can place here. Okay, so what we shall do is we shall put 6 here and make this point to the top of the stack of the previous stack. Okay, 6 is done. Next we shall see 7. Okay, 7 we cannot put here, not here, not here, not here. So what we can do is create a new stack with 7 and make this 7 point to the top of the previous stack. Okay, now we take 1. Okay, now we cannot place 1 here because this top is not greater than equal to the current, but you can place 1 here. We can this points to this. Then we take 4. We cannot place 4 here, not here, not here, but we can place 4 here. Okay, and this points here. Now we are done. So the number of piles which we get gives us the length of the increasing subsequence. Okay, now how we can get the increasing subsequence? Uh, take 7. Uh, this is the example. Means first we get 7. For following that we get 6. Then we get 3. Then we get 2. Then we get 1. So we are getting a subsequence of 1 to size 5. Okay, length 5. How it is that 1 is there, 2 is there, 3 is there, 6 is there, 7 is there. So we are getting a subsequence of length 5 from here. Okay. chains of subsequences. Okay, means what is that? Means these stacks and their pointers, they can form parallel chains of longest increasing subsequences. How? Means let me show. Let us consider it in this manner. The thing is that when we are executing this, when we have seen this one, and when next we are seeing this one, okay. Now this one cannot form. Means okay. Means let me take another example. It shall be better. Okay. So since two ones are there, it shall create confusion. Okay. So see, when four is there, we might have done something else, so that means we can think that since 4 is there, why are we putting 3 here? Means actually the thing is that this 4, although this 4 is here, this putting this 3 here, we are doing something such as we are creating a parallel subsequence. Okay, means this forms one subsequence, these 3 forms another subsequence. Now why are we putting 3 in this within this form? Is there is no chance of increasing this subsequence which ends in 4. Why? Because this, see, when we are getting this 4 and after that we are getting this 3, so definitely whatever subsequence we have formed using 4, we cannot extend it by adding 3 to it. So 4 and 3 are at the same parallel level. Okay, means whatever 4 can do, 3 has that capacity, but in a parallel pathway. Means they cannot increase the pathway in a serial manner. Okay, I hope you can understand what I am saying. So similarly, if you see 10, okay, we have put 10 first here. Now see 6 and this 4. Okay, now the subsequence which 10 is forming, that is 1 2 3 1 2 3 and 10. Now after that, on seeing a 6, we cannot possibly increase this 10, means the subsequence which is formed using 10. So they are a part, means they are forming a chain in a parallel manner. There, which instead of 10 we can choose 6 and proceed in a similar manner, but we cannot as such extend 10. That is the thing, is putting the elements in one stack, which means that they have the equivalent capacities regarding the increasing of chain length, regarding the increasing of chain, as far as the increasing of chain length is concerned. Okay, so that is the thing. I don't like if I explain more, it shall be like over explaining the concept. Let me check. Let me take another one. Okay, no, rather there is no use, because it shall over confuse things, because two twos are there, means it shall create a confusion. Okay, now I guess means putting the elements in the stack in this manner is clear now. Means they are forming a parallel chain, means parallel chains of uh, long increasing subsequences. Okay, now the thing is that means if you just try to convince yourself as to how this uh, concept of maintaining parallel chains of increasing subsequence is working, then it shall be clear that we are creating another stack only when it is absolutely necessary. Okay, means when we have created this stack containing 10, we couldn't have placed it here, means anywhere here, and when we are putting it here, it is definitely because it shall increase the chain length. Okay, now this 6 and 4, when they are placed here, they couldn't have been possibly placed in some other stack such that they could have increased the length. So this is the optimal way of is arranging the elements in a pile of stacks. Okay, to create so that such that they shall give increasing subsequence. Okay, longest increasing subsequence. Now, one problem which we are having here is that though we have got the increasing subsequence up to 1, 2, 3, 6, and 7, but if we see here, the increasing subsequence which monotonically increasing subsequence which we can get here is 1, then 2, then again 2, then 3, then 6, 7. So we can get a subsequence of length of 6. Okay, what is that? 1, 2, 2, 3, 6, 7. So what is the problem which we are having here is that we are putting when we are seeing another element, we are putting it inside, means in the same uh, chain, means same stack. Okay, means same stack we are putting it, but this shouldn't have been the case if we are wanting to increase the chain length where there are two consecutive twos can be there. So what we can do here is that when we are inserting an element into means into the one of the stacks, we shall see. We shall first check for the equality. Okay, means when we shall see that there is an element which is already present in the stack and top of the stack and having the same value. Okay, of the current element which we are scanning, 2 for instance. See this. Okay, 2 for instance. Then what we shall do it, instead of putting it in this one, means the same stack, we shall put that element in the next stack. Okay, means if there is a chain of okay, means this shall be clear if we take an example. Means instead of putting it into the same stack, we shall put it in the just the next stack. Let me clear this up a little bit, then we shall proceed with the modified example, which shall help us give longest monotonically increasing subsequences. Okay, here put forward few important things which are required to implement the algorithm in programming language as well. Okay, so it's to keep track of the elements, which what we can do is that we can create another, say, an array. Okay, here, which shall hold pointers to uh, the elements of the subsequence which we are forming. Okay, the parallel subsequence which we are forming, the pointers which we are keeping in the stack, we could have directly kept it on a separate array using this, which shall help us give the pointers. Okay, so means how I guess you can understand, means suppose this is index 1, this is index 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Suppose for example this 7 points to the element 6. What we can do is to do that is, in corresponding to this index we can put 9. Now when and if this 6 points to the element number 3, we can place here 5. So in effect what is happening is that this 7 is pointing to this 6 and this 6 is pointing to this 3. So this is the thing. I shall go into the details of this detail a little later, but let me first take up the example which I was going to explain using this stack. Okay, first where we shall be having monotonically longest increasing subsequence. Okay, the element 1. Okay, so there is nothing. We have a scratch, means blank scratch pad. Okay, so we take a stack and put 1 inside it. Next, when we have to see 2, we cannot place 2 here. We create another element. Okay, and make this 2 point back to 1. Okay. Now this is a hypothetical thing which I am working out, but what we can actually do is that in that array which I have already shown, we can make these 2 point to this one here. Okay. And why it is necessary, because we might not even desire to maintain stacks like this. We can only keep the top of the stack at any instant of time. Means in our memory we can have this top and this top, and as we proceed we shall only have this top. So in the previous example, where we were having those stack, means the other elements of the stack were pointing to the pointing to elements of the previous stack. Since we are keeping only the top of the stacks, so it might be a bit difficult to maintain that. So we are keeping the pointers to the elements in this manner using a defined index array. Okay, yes. Keeping that effort, let's continue with our example. Okay, now we have 4. We cannot place here, we cannot place here. We create another array. Okay, this is 4. Now let me this points to this element 2. Okay, now this here, it points to this element 2. Now we are at this 2. Okay, now what we can do is, see, this in the previous example we could have put 2 here, but now what we shall do is that we shall put this 2 here and make these 2 point back to this 2. So how we shall do it? Make this 2 point back to this 2. Okay, now next we shall take this 3. Now this 3, where we can put it, we cannot put here, not here, not neither here. So what we shall do is we create a new stack and make this 3 here, put this 3 here, and make this 3 point to this 2. So effectively what we are doing here is that we are pointing this here. Now when we have 1, what we can do is we shall put it here. Okay, it would have been put here, but what we shall do is we shall put it here and make this 1 point back to this 1. Effectively what we shall do is we shall make this 1. Sorry, we shall make this 1 point back to this initial one. We shall make this 1 point back to this initial one. Okay, make this 1 point back to this initial one. Now we have 10. We cannot put 10 in either of these stacks. We create a new stack for this and we put 10 here. Please bear with me for this diagram. I am drawing with the usual mouse which we have. Now we shall make this 10 point to this 3, top of the stack of the previous stack. Now this 10 points to this 3. Now we have 0. 0 we can easily put here. Okay, no issues with that. Then 6, where we can put 6, we can put 6 here as per our working example. As per our example, this 6 points to this previous 3. So similarly, this 6 points to this 3. Okay, now we have 7. 7 we cannot put in any of these boxes, stacks. What we shall do is we shall create a new stack and put 7 in here. Okay, and make this 7 point to this 6 and make this 7 point to this 6. Okay, now we shall see 1. Okay, this 1 we shall see. Currently it could have been, see, we are having actually a peephole window. Okay, peephole sort of window. What we can actually see is that at only the top of the stack we can see. Okay, we can see 0, we can see 1, we can see 2, we can see 3, we can see 6, and we can see 7. Suppose in an array named top of the stacks. Okay, so on seeing that, we see that in stack 1 suppose this is okay, see this is stack 1, this is stack 2. We see that stack 2 is having a top of the stack as 1. What we can do is we get the next stack, which is stack 3, okay, and replace its top with the element 1, okay, and make this one point to the previous top, okay. So what we shall do, shall make this one point to this previous one. So this is done, and we have this 4, but we cannot place in any of this one. We put 4 here, and make this 4 point to this 3, and out of space, and make this 4 point to this 3, okay. So when we are done with this algorithm, what we shall have is, we are having the number of stacks which we have got gives us the length of the longest subsequence, okay. So 1 2 3 4 5 6, we are having a longest monotonically increasing subsequence of length 6. Now if we follow the pointers back, we have 7, then we have 6, then we have 3, then we have 2, then we again have 2, then we have 1, okay. This, see, when our algorithm means, if we are implementing the means algorithm using that people concept where only the top of the stacks are maintained, this thing, this, and this shall only be there in our memory. These things shall not be there, okay. This shall not be there, this shall no longer be there, this and this. Only the top of the stack shall be maintained. And when we are seeing that we have 7, what we can do is that we can create, means along with this 7, we can have an index to the actual array, okay. Means we can have an index to the, means the actual array index, we can have this 7 might point to this 7. Yes, we can have an index, and using that index we can first print 7, and then go to follow this index and go back to the pointer where this 7 is pointing, then 6, then using this 6 we can go back to 3, then using 3 we can go back to 2, then using this 2 we can go back to this 2, and using this 2 we can go back to this 1, okay. So why it is taking a time of n log n? Why? Order of n log n, why it is taking? So the main point is that we need to scan this array, okay, in totality. So that adds to time complexity of order of n. Okay. Now at any instant of time, we shall be having a pile of stack tops, means an array of stack tops, and where we shall put that means the new element where in which pile we shall put in. We can easily check it using applying binary search on the stack tops, and we can have a pile length of at most, okay, at most we can have a pile size of at most n, and applying binary search on them shall cost us log n, okay. So in order of n time, means order of n time to scan these, each of them shall cost time log n. Sorry, each of them shall cost a time of order of log n. So in totality we shall have a time of order of n log n. Hope this makes the things clear. I have just tried to explain it in a means informal manner. No means rigorous proofs or anything. Just the concept shall be clear. That was my main aim, and coding shall be easy once this concept is known.